Hello everyone, my name is John Bozard and this is my Physics 2211 Lab 3 on black holes. The goal of the experiment is to use Glowscript and physics principles to estimate the mass of the black hole given the change in time, 1 day or 86,400 seconds, the star's mass 2.0 times 10 to the 30th kilograms, and a randomized position vector for the star. The net force on the star is due solely to the gravitational pull of the black hole. To the right, you see a simplified model of the lab. The star is the system and the black hole is acting as the surroundings. The star is orbiting counterclockwise and the purple and green vectors correspond to the parallel and perpendicular components of the net force in blue, respectively. Newton's second law, force equals mass times acceleration, can be manipulated into the momentum principle by substituting delta p over delta t for acceleration. Newton's law of gravitation says that the gravitational force between two masses is equal to negative g times m1 times m2 over magnitude of the position vector squared times the norm of the position vector, where g is the gravitational constant 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared. The rate of change of momentum is extremely important in this experiment and can be written as dp over dt equals change in the magnitude of momentum over change in time times p hat plus magnitude of p hat times change in p hat over change in time. The parallel component of the net force is equivalent to the first part of the above equation, and the perpendicular component of the net force corresponds to the second half of the rate of change of momentum expression. The seed is unique to my email and determines the star's trajectory. I proceeded to plug in the given values of the star's mass and delta t. On the right, the initial and final momentum values are found by multiplying the star's mass by the initial and final velocities. After the momentum principle and Newton's second law are coded, the parallel component of the rate of change of momentum can be calculated. First, I determined p hat, which is the unit vector for the star's initial momentum. Then, I multiplied this value by the change in momentum's magnitude over time, which results in dp over dt parallel. Using Newton's second law of gravitation previously defined, I solved for the mass of the block in terms of variables that Glowscript can find. The r value on the right is the magnitude of the position vector, which is simply the magnitude of the star's initial position because the black hole is centered at the origin, so no components change upon vector subtraction. I cannot use f perp equals mv squared over r because the star does not travel in a perfectly circular motion. The mass of the black hole is isolated and equal to the magnitude of the position squared over the star's mass times gravitational constant g. After running the Glowscript code and averaging all of the mass values in Excel, I determined the mass of the black hole to be 8.02 times 10 to the 33rd kilograms. Here's another quick look at my code. In case you want a closer look, the link is in the description of the video. If the program is run, you can see the elliptical path that the star takes around the black hole. Notice that as the star gets closer to the hole, the force vectors increase in magnitude and vice versa. This is because in the gravitational attraction equation, the magnitude of the distance r between the two objects is in the denominator, so when this value decreases, the overall net force increases. The parallel component of the net force in pink is always in the positive or negative direction of the ball's motion, and the perpendicular component in blue is always orthogonal to the parallel vector. As a result, the net force vector points in between always in the direction towards the black hole, because the only force present is the gravitational pull. So how is the net force different from the rate of change of momentum? Well, numerically they are the exact same. However, in this lab we are unable to calculate the net force independently because the mass of the black hole is unknown. Therefore, the star's initial mass and velocity must be used to determine the change in momentum over time, and the mathematical equivalency between dp over dt and f net must be assumed. If a new black hole takes the place of the original at the origin, and the star's trajectory and mass don't change, is it possible to calculate a different mass for the black hole? The answer to this question is no, because the black hole's mass is dependent on the star's motion and mass, both of which stay constant during the black hole switch, so when calculated, the value of the black hole's mass will be the same.